Finally, let's take a look at a complete numerical example. In this case, again, just like the Google PageRank lecture, we are constrained to a slide or a page, and therefore the examples do not represent the challenge of scale or sparsity. If you recall, scale and sparsity were the big challenges for Netflix price. So this only really serves the purpose of illustrating the 5 steps that we just outlined for neighborhood method. Here is our starting point. We are given, these are given constants, the rating information. Each entry of this big matrix R is RUI. And you see that this is 10 user by 5 movies. Label users 1 up to 10, and movies A up to E. And it is 80% filled. Okay, so 40 out of the 50 possible entries already actually known. This is again very atypical. Generally speaking, only about 1% instead of 80% of the entries are filled in a typical real data. But if we only have 1%, then we don't even have a single entry of known data in the training. Now, 10 of these are represented by bars. This means that rating simply does not exist for that user movie pair. And now we're going to say, let's hide 10 out of the 40 known data as test data and use the remaining 30 as training data. So 30 samples for training and 10 to test our prediction. So somewhere arbitrary, let's just pick these circled 10 entries as test data. Okay, so we know, but we just pretend we don't first and train with the remaining 30 points and see how we do on these 10 points. First of all, the very lazy R bar, in this case 3.83. In Netflix case 3.6. All right, step number 1, baseline predictor. Let's construct the baseline predictor, which is R hat UI equals R bar 3.83 in this example, plus a bunch of biases for each user for each movie, and this holds for all the UI pairs. Okay, so we got how many? 10 of these parameters and 5 of these parameters. Got 15 parameters in this case for the baseline predictor. And we're going to pick the right baseline predictor parameters BU star BI stars by solving a least square problem. The least square problem is, as you'll recall, AB minus C L2 norm squared. We minimize this, and the solution is A transpose A times B star will be equal to A transpose C. So what are the A, B's, and C's? The B is easy. That's our 15 optimization variables. These parameters under training, B1 up to B10, and then BA up to BE. What about the matrix A and vector C? We simply construct those, and like what we did in the small 2 movie 1 user example before. In particular, this A matrix is gonna to be we have this 15 by 15, we have a 30 by 15 matrix. 30 because we have 30 training points starting from R1A to R10E. Okay, so basically all the points here that are not red circled are our training data. Okay, and we have therefore 30 equations and 15 variables corresponding to B1 up to BE. And the tables basically this matrix A is 0, 1 binary, is 0 everywhere unless we're talking about that particular user and particular movie. Say in this row, the first equation out of 30, we're talking about R1A as the training data. So we have to write a 1 where it corresponds to B1, the first position, and the 11th position, which is corresponding to the BA position. And the C vector is simply the known training data R1A down to R10E, subtracting the R bar. So now that we have defined A, B, and C, we can use this equation as the solution to this least squares problem, and the resulting solution, BU vector star and BI vector star, are just partially shown here. This is 10 entries, this is 5 entries. And then you can stick these back into the predictor here with the optimized BU, BI by training, and then you got the baseline predictor. Okay, that's step number 1. Now we can, for sanity check, verify. In the textbook you see all the entries, but here you can see indeed BU is quite positive, B1 is quite positive, and BA is also quite positive. That means user 1 tend to give high scores, and movie A is well liked. So just to make sure that's the case, indeed user 1 tend to give high scores, and movie 1 is well liked. Okay, a lot of 4s and 5s. So the bias computation is indeed making some sense. Step number 2 is the prediction on the baseline. So the baseline predictor, using the optimized BU, BI, and the average R bar, will give you this prediction. Okay, we call this R hat. If you look at this R hat, and remember, some of these are training data, some are test data. So these, for example, are the test data. Okay. And let's compare with the actual data, RUI, for say these 5 out of the 10. What do we have here? We have 5, 3, 2, 2, 5. Those are the actual RUIs that we were hiding from ourselves. Now that, let's see, 5, 3, 3, 2, 1. 5, 3, 2, 2, 5. 5, 3, 2, 2, 5. 2, 2, 5. Are they close to 5, 3, 2, 2, 5? Yeah, reasonable, I guess. 4.62. If you round up, it will be 5. But if you compute RMSE, then there is a difference of 0.38. 3.49 versus 3. This is getting a little off. Half a star off is quite off, actually. And if you, depending on how you treat this 3.45, you may round it to 4, and then you actually incur a significant error. And even without rounding, this difference of 0.49 is also quite big. This difference is huge. It's between 2 and 2.78. This difference is also big, and difference is quite small. So we pretty much get this quite right, this quite right, this sort of reasonable, but these two predictions are kind of not that good. Okay. One way you can deal with this is to use regularization to avoid overfitting in the advanced material. But in general, baseline prediction doesn't leverage any collaborative filtering techniques of global structure, so we're not doing very well. But we're not done yet. So at the end of step 2, we shift R by R hat, and we get R2D matrix. I'm just writing down the R2D matrix 2 columns out of 5 corresponding to movies B and C respectively, because we're going to use this to illustrate now step number 3, which is construct the similarity matrix D, where each entry is Dij. Let's look at a particular example. Let's say we look at the movie BC. Okay, this is movie B, this is movie C. Let's look at, out of the 10 users, how many users have already rated both movies B and C? Well, that's 1. User 1 rated both, user 2 rated both, but then you got other users, either they have not rated some movie or they have rated, but we can't use those for training. Those are for testing. So we have to go all the way down to the user 9, who actually we have data of user 9 rating both movies B and C. So we got 3 users, 1, 2, and 9, that rated both movies B and C, and therefore can be used to compute the distance between movies B and C, the cosine similarity coefficient. So we're looking at basically 2 vectors, 0.91, 0.11 minus 0.87, and 0.9, 0.31, and 0.33. And we'll look at the difference between these two vectors by looking at their inner product. So 0.91 times 0.9. Oh, I'm sorry, this is minus. I should say minus. Okay. This is also minus. So minus 0.9 plus minus 0.11, 0.31 plus minus 0.87 times 0.33, and then I have to normalize. So the square root of 0.91 squared plus 0.11 squared plus 0.87 squared times 0.9 squared plus 0.31 squared plus 0.33 squared, and this is the formula for cosine similarity coefficient dBc, which turns out to be minus 0.84. So notice these entries are negative because after shifting the rating from baseline predictor, sometimes is positive or negative relative to the baseline predictor. And these coefficients of similarity are sometimes negative because the two movies are dissimilar from each other. And these two are indeed quite dissimilar. Okay, it's minus 0.84. It's quite close to minus 1. So we can say movies B and C are quite dissimilar. Now we can do this now for all the pairs of movies to come up with this entire matrix D here. The diagonals doesn't matter, so just cross them out. The off diagonals are symmetric because the way we define it, dBc equals dCb. Okay, and indeed this is dBc or dCb, same thing, is minus 0.84 as we just calculated, and you simply follow the rest of the same structure for the rest of the entries. That's the end of the step 3. We have constructed similarity matrix. Now step 4 is to define a neighborhood. Let's say a neighborhood for any movie is just 2. Okay, so the top 2 movie with the absolute value Dij being the largest relative to movie J will be included in the neighborhood. So let's take an example. For example, let's say R hat 3D. We want to estimate user 3 rating movie D. Remember, user 3 rating movie D, we did not have that actual information. As we can see here, 3D is one of those that we were hiding from ourselves, so that now we can predict, see if we can get to 2. Okay, so we want to find out what is R hat 3D based on the neighborhood method. Well, first of all, there is the R hat 3D baseline predictor component, then there is the neighborhood prediction component. This happens to be 2.78. Now what is this? Since we decided the neighborhood consists of 2 movies, so for movie D, what are the top 2 similar or most dissimilar movies? This is for movie D, and we can see that movies A and B are most similar or dissimilar in the absolute Dij terms. Actually, both are very dissimilar. A and D are very dissimilar. Okay, so we have used so far the information about different people's tastes on these movies. A, this is A up to E, right? A down to E, between movies D and A and B. And then we take that information, okay, the fact that A and D are very dissimilar by people's record, and B, D are also quite different by people's record, as a way to say that therefore A, B should be incorporated as we predict anyone's prediction liking or disliking movie D. So following our formula, we have minus 0.97 times the weighting, while the weighting turns out to be the prediction of the rating of user 3 on movie A. Okay, plus minus 0.73 times the rating of user 3 on movie B. And this happens to be 0.9 in the shifted domain, and this happens to be minus 0.19 in the shifted domain. So in particular, we see that the same user 3, whose taste on movie D we're trying to predict, really liked movie A. But since A and D are very different kinds of movies, that's so dissimilar, that means she will very likely not like movie D. This is a big positive number, this is a big negative number. The overall impact is to make this R hat 3D n to be a very small number. And then we just normalize now by the absolute value of the Dij, which is 0.97 and 0.73. This therefore happens to be 2.35. In other words, the net effect of the neighborhood help is to reduce the prediction from 278 to 235. The actual answer is 2, and indeed, in the baseline predictor, it overshoot 2 by too much, very close to 3 stars. Whereas with the help of neighborhood, knowing that A and B are very dissimilar from movie D, and user 3 kind of likes A and doesn't hate B too much, which actually tells us that she is going to really not like D a whole lot. With that information, we push 2.78 down to 2.35, which is indeed much closer to the actual ground truth 2. If you compute the squared error between 2 and 2.78, you see that's much bigger than that between 2 and 2.35. So now we can compute this for all of the 10 items that we want to predict. And it turns out that we get a much better improved performance. In the baseline predictor, R hat, we get the error of 0.51 and 0.58 respectively for the 30 known training data and the 10 test data. But this get improved into neighborhood predictor R hat n, where the overall root mean square error for the training data is as small as 0.32, and for the 10 test data is also smaller, 0.54. Again, it's what these 10 predictions that really matter in Netflix price. You may think these are very small numbers. Again, in the scale of up to 5 stars, half star is a big deal, and even improving on the next digit is often going to make a big difference in what we recommend. And that's what the 10% goal of Netflix challenge is trying to do here. This represents a 7% enhancement by neighborhood method over baseline method. And it turns out that if you use neighborhood method plus temporal dynamics plus regularization idea of least square plus a couple of other tricks, you can easily get to almost 9%, meaning you can actually win the first entire year of progress prize and more of enhancement over the sign match. But getting the other 1 or little over 1% to get to 10% target of enhancement over sign match took 2 more years of effort by many smart people around the world. Thousands of teams, tens of thousands of different submissions, and 2 years time to enhance that 1 to 1.5%. That's why a lot of people believe that had Netflix set this to be 11 or 12%, it may not even be achievable using the known data. That we will never know the exact answer. But what you have seen so far, with a few tricks, get you quite far in that price if you were participating back in 2006. So that's the end of this longest lecture in the entire course. We looked at Netflix Prize, a very interesting scientific story as a special case of recommendation system. In particular, look at how collaborative filter leverages similarities among users, or, as in our example, among movies, to enhance the accuracy of prediction, say measured by root mean square error. And if you indeed minimize root mean square error, which you don't have to, as we saw, this will lead to often a least squares problem, which is a special case of convex optimization that we see over and over again in the course. This is just a very brief terminology introduction on convexity today. So this lecture is long in part because not only we're talking about collaborative filtering as a learning idea, but also start to introduce convex nonlinear optimization. It's also long in part because Netflix Prize is a very interesting story to show the timeline and some details of the competition. Then this special case recommendation system will lead us to the next lecture, lecture 5, on recommendation system on Amazon in a different context and a different question over there. So see you